Alright, so we're going to be taking a look at section 15.3. 15.3 deals with double integrals and polar coordinates. So you might look at this and say, why do we need to figure out how to do double integrals and polar coordinates? And part of the issue is that you might be integrating a function over a given region that's a real pain in the neck to describe using rectangular coordinates. And it could very well be that polar coordinates are really, really useful to describe the region. And I'll give you a little bit of an example here. So let's suppose that you have maybe a circle of, let's go with radius 2. Centered at the origin. So what's going to happen here is if you have a circle of radius 2 centered at the origin, we know that x squared plus y squared equals 4 is an equation for that circle. But if you solve for y, of course we get y squared is 4 minus x squared. So y would be plus or minus square root of 4 minus x squared. Now, of course, the positive root 4 minus x squared gives you the equation for the top half of the circle, and the y equals negative root 4 minus x squared gives you the equation for the bottom half of the circle. So if we were to call this region D, for example, then the way we would describe D, or one way we could describe D, is to say, well, this region lies over an x interval from -2 to +2. But we don't want to say that it lies also over a y interval from -2 to +2, because then that would basically just give us a square as our region, and clearly we don't want that as our description. So we have to think about, well, while x is ranging from -2 to 2, y boundary up top is going to be the square root of 4 minus x squared. On the bottom it's going to be negative square root of 4 minus x squared. And so think about if you're trying to integrate some sort of function over this circle and you're stuck using rectangular coordinates, then these are going to be limits of integration with respect to y. -2 and 2 would be limits of integration with respect to x, which isn't so bad, but you might not want to deal with these. So what we could do instead is we could say, well, if we think about representing this region in terms of polar coordinates, we could say that D is going to be described so that r ranges from 0 to 2 and theta ranges from 0 to 2 pi. Because we are doing a full revolution, and every single point that's in this region D is going to be from 0 to 2 units away from the pole. And so when you take a look at integrating, let's say with respect to r and theta, limits of integration are really nice. They're all constant. And so that could lead us to some really fortunate circumstances with integration that we wouldn't quite get if we're taking a look at using rectangular coordinates. So that gives us a little bit of a motivation as to why we might want to pursue this idea of using double integrals in polar coordinates. Now, keep in mind, it's going to be useful for us to remember some of the conversion equations that we had. So if you think about x squared plus y squared equals r squared, that's one of the conversion equations we have when going from rectangular to polar coordinates. We also have x equals r cosine theta, and we have y is equal to r sine theta. So these are convenient equations for us to kind of keep in mind as we're working with these transitions from, let's say, rectangular to polar coordinates. So we're going to take a look at a certain definition. We certainly know what a rectangle looks like in terms of Cartesian or rectangular coordinates, but we could also think about this idea of a polar rectangle. And so that's going to be our next definition, is what exactly is a polar rectangle. So let's suppose you have a region. You're going to call it R, and I think I'm going to put R here. So R is going to be a set of all points. First coordinate R, second coordinate theta, such that we're going to have constant bounds on R, and we're going to have constant bounds on theta. So the bounds on R that we have, we're going to call A and B. And the bounds on theta we have we're going to call alpha and beta. So constant boundaries for both r and theta, that's pretty nice. This is what we refer to as a polar rectangle. And so you might think about, well, I'm not so sure that this really represents a rectangle. It certainly doesn't look like it from the traditional sense. But if you think about what region this is actually describing, we could say, let's suppose we have a set of axes like so. And maybe we have theta equals alpha over here. Maybe we have theta equals beta sitting right there. Maybe we have some sort of r equals a sitting right there. Maybe we have an r equals b that is right here. So the region that we would be describing would be this region that's in here, between the two radial lines, theta equals alpha and theta equals beta, and also between the two circles, r equals a and r equals b. Now you might look at this once again and say, well, this doesn't really look like much of a rectangle to me. However, if you were to think about having some sort of r-axis and some sort of theta axis, like the following. Say this is an r and this is a theta, then you could have r ranging from a to b, you have theta ranging from alpha to beta, and then what you would have from this perspective would actually look like a rectangle. So, although it doesn't really look like a rectangle in the traditional sense here, we could do a transformation and produce this rectangular form that we see with an r-axis and a theta axis. Now, the question is, what happens if we want to integrate some sort of function over a region that looks like this? Now, when you start to think about what we do in previous sections, we start to think about, well, how do we exactly integrate over, let's say, a rectangular region? That's something we looked at in section 15.1. Well, let's say you have some sort of rectangular region. We'll have x ranging from a to b, and we'll have y ranging from c to d. Okay, so we might have a picture look something like this. And then what we want to do, let's say, to try to figure out an estimate for an integral of some function f over this rectangular region, we might start thinking about, well, we could partition this rectangular region into subrectangles. So maybe we have a picture that looks kind of like this. And then from each of the subrectangles, we could take a representative point, plug that point into the function. We would get, if we're thinking about some sort of z equals f of xy that's sitting over this rectangular region, we could start thinking about, well, what is the volume of the solid that sits over this rectangle and is capped by that z equals f of xy. So when we take representative point from each one of these different subrectangles, we plug that representative point into that function f of two variables, and that'll give us the height of a rectangular solid sitting over the particular subrectangle. Take the height times the area of the subrectangle, gives you the volume of a rectangular solid. That sort of approximates what the actual solid region is going to look like over that particular subregion. You end up adding all of the volumes together, gives you an approximation for the double integral of this function f of xy over the rectangular region. Now, when you start to think about these different horizontal line segments and vertical line segments, what you have to keep in mind is each of the horizontal line segments is part of a line of the form y equals a constant, while each of the vertical line segments is part of a line of the form x equals a constant. So if we were to take a look at a partition of a region like this, in terms of polar coordinates, then we could think about, well, what would the partition look like if we were to take r equals different constants between a and b, and theta equals different constants between alpha and beta. And so if we were to do something like that, then what would happen is we would get a whole bunch of different radial lines, perhaps, between theta equals alpha and theta equals beta. and then a whole bunch of different circles that would be between r equals a and r equals b. And so you'd have a picture that looks something like this. And so now we have this original region that was sitting right here. And then we can start thinking about, well, what if we were to take certain representative points from the different pieces of this partition? Now, what you have to keep in mind is that these pieces aren't rectangles. These pieces are actually parts of sectors of circles. So, for example, if I were to take a look at, let's say, this subregion right here, it's not a rectangle, but we could say that it approaches the shape of a rectangle as the radial lines get closer together, as the radii get closer together, as the distance between these two radial lines angle-wise is tending towards 0, and so forth. We could say that, yeah, this is approaching the shape of a rectangle, but it isn't actually a rectangle here. But what we could do is we could still come up with, let's say, a representative point from this particular subregion, plug it into whatever our z equals f of xy is, let's say, and integrate over this polar rectangle that we have here. So we start to think about, well, what would a typical representative point look like? And I guess what we need to do is we need to start thinking about, well, what would the boundaries here and here be? And what would the boundaries here and there look like? And so what we're going to do is we're going to end up taking a look at, let's say, this will be our r equals r sub I minus 1. And this will be some sort of r equals r sub I. And then this radial line will have theta equals theta sub j minus 1. And then this radial line will have theta equals theta sub j. And we start thinking about, well, what would the point, let's say, right in the middle of that subregion look like? And if we start to think about what that particular point might look like, well, let's first of all locate it, right? It's got to be somewhere around there. And then we start to think about, well, maybe, just maybe, this would be some sort of point r sub I star theta sub j star in terms of polar coordinates. Now, if we're really going to start talking about what it means to, let's say, evaluate a double integral over some sort of polar rectangle like this. Imagine a situation in which you have some sort of z equals f of xy sitting over this region. You've partitioned this particular region into subregion. That's good. That's what we want to do. But the idea here is that we take a representative point from every single one of these subregions, plug it into that z equals f of xy, and that would give us, let's say, the height of some sort of solid region that has a base that looks like this. But we would have the certain height, once again, given by this, plugging this point here into our function. And so what we could do is we could say, let's take a look at all the volumes of those rectangular solids, let's add them all together, and then that would give us an approximation for the volume of the solid that's capped by our function of two variables, and also bounded by, has a base that's equal to this polar rectangle. And we could get the partition finer and finer and finer. We could get our volumes closer and closer and closer to the actual volume of the solid region that was described. Now, here's what we have to think about. How exactly is it that we would find the volume of such a rectangular solid? Well, plugging this into some sort of function f really isn't the hard part. And I guess the next part really isn't that hard either, but we have to consider what the area of a subregion like that would look like. Well, with that in mind, let's think about what the area would be. And so let's take a look. At what the area would end up looking like. Well, let's think about this for a moment. What you have here, distance from the pole to here is actually going to be your r sub I minus 1. Distance from the pole to here is actually going to be your r sub I. But there's also an angular distance between here and there that we're going to refer to as delta theta. Now, if we're interested in figuring out the area of this particular subregion here, then one thing we could do is we could take the area of the entire sector here that's bounded by this r sub I, and then subtract away the area of the sector here that's bounded by the r sub I minus 1. So once again, take the area of this sector that's bounded by the r sub I, take away the area of the sector that is bounded by the r sub I minus 1. Now the great thing about this is you got the same central angle delta theta, so no big issues as far as that goes. But we have to start thinking about, once again, what is that area going to look like? Well, remember, if you take the area of a sector of a circle, what you want to do is take the central angle divided by 2 and multiply by the square of the radius. So the angle, as I mentioned before, that we're going to be taking a look at is going to be delta theta. The area of this sort of outer sector, I guess you might call it, would then be 1/2 delta theta times r sub I squared. But then we have to subtract away this extra area here that we don't want to have because we just want to limit ourselves to this little area of the partial sector. And so what we would do is we would say, well, this particular sector has an area that's equal to 1/2 delta theta times r sub I minus 1 squared. So this subtracts away the extra area from this outer sector that we really don't need, and it leaves us with the area of that little subregion. And so that really works out well for us. Now, to take a closer look at this, we notice that this area is actually going to be equal to, well, you can factor 1/2 out, you can factor a delta theta out, and what you'll have is 1/2 times r sub I squared minus r sub I minus 1 squared times delta theta. Okay, this r sub I squared minus r sub I minus 1 squared is the difference of two squares. We can factor it. And so if we think about what the factorization would look like, well, you'd have this 1/2 times r sub I plus r sub I minus 1 times r sub I minus r sub I minus 1. And we still have the delta theta sitting right there. Now, something interesting to keep in mind is that the r sub I minus r sub I minus 1 is simply the distance between the two radii we have here. Now, in this partition, the distance between the radii, we're calling delta r. Also, keep in mind that when we take a look at the 1/2 times r sub I plus r sub I minus 1, we're actually taking the average of the two radii here. And so, with this in mind, we could say, well, that average radius that we have, we're just going to call that r sub I star, because once again, this point was halfway, it was right in the middle of this region, so it's going to be halfway in between the two radii. So we'll have the r sub I star, it's going to be the same thing as our 1/2 r sub I plus r sub I minus 1. The ri minus ri minus 1 is going to be delta r, and then we'll have delta theta that is here at the very end. So that would be what we could use to refer to the area of that little subsector, or subregion, I guess you might say. Now, where do we go from here? Well, let's keep in mind that the idea is going to be to take a double integral of some sort of f of xy over some sort of polar rectangle like so. And so we start to think about what exactly would that look like. Well, as a result, we're going to have to take a look at putting this point into this f of xy, but you don't want to put in r sub I star and theta sub j star for that. Because if you have, let's say, z equals f of xy as the function you're integrating over this region, you're going to want to put in an xy, not an r theta. So if the point here is given to us in terms of r sub I star and theta sub j star, then what we have to do is go back to our conversion equations. So then our x would actually be r sub I star times cosine theta sub j star, and our y would be r sub I star times sine of theta sub j star. So that would be what we would end up putting into our locations here for x and y. That's going to give you the height of some sort of solid that's sitting over this little subregion here. And we already have an idea as to what the area of the region is because we just figured it out. So if we think about, let's say, the area of this being some sort of delta sub AI, we'll incorporate that in our next representation. So think about this for a moment. This idea of putting solids over each one of these subregions is going to mean that you're going to be adding up a whole bunch of different volumes of solids. And so the way we're going to do this is we're going to have a double sum. So we'll take a look at the summation I equals 1 to n, summation j equals 1 to m, and then we're going to have this f of xy, but once again, we're not plugging in x and y. We're going to be plugging in r sub I star cosine theta j star. So that'll be our x coordinate, but then we'll also have r sub I star times sine theta j star. Now that'll give us the height of that solid, but let's keep in mind you also have to multiply by the area of the base of that solid. And so that'll be our, we'll call it delta A sub I. All right. Well, here's where that leads. That's going to be the same thing as the summation I equals 1 to n. The summation j equals 1 to m. We'll have the f of r I star cosine theta j star r I star sine theta j star. So remember our delta A, that's r I star delta r delta theta. Now suppose that what we do at this point is we define some sort of function g. So maybe we define some sort of g of r theta. But let's say that that's the same thing as r times f of r cosine theta comma r sine theta. So if we define our g of r theta this way, then let's think about how this is going to get affected. Well, you've got your, if your r is, let's say, ri star, and your theta is theta j star, then you're going to have an ri star here, which is going to match up with that. You're going to have f of ri star cosine theta j star. Okay, well, we got a matching here. And then ri star sine theta j star. Okay, we got a match. That's good. So you're going to have the summation outside I equals n to n. And then we have summation j equals 1 to m. And this will be g of r I star theta j star times delta r times delta theta. Now, let's think about what that means in terms of our double integral over some sort of region R. And what we're going to be integrating is this f of xy. Let's think about what that is actually going to equal. So we'll go over here. And then what we'll have is this double integral over R of f of xy dA. Well, that's going to be the limit as both n and m approach infinity of the summation that we're seeing right here. But check it out. This we already said was the same thing as this double summation of g of ri star theta j star delta r delta theta. But if we go back to what we saw in previous sections, we know that this is going to be the same thing as our double integral. In fact, we'll have alpha and beta as limits of integration on the outside, a and b as limits of integration on the inside. We'll have a g of r comma theta dr d theta, which will be the same thing as, going back to what we're seeing here, double integral of f r cosine theta comma r sine theta r dr d theta. So this part actually is going to be corresponding to our original differential of a. All right, so this leads us to the following theorem, which I'm about to put up on the board. Let's say we have a continuous function f. Once again, continuous function f on a polar rectangle R. And so we're going to see how we're actually going to define R. So this is going to be given by, we'll have a greater than or equal to 0, but a is going to be our lower bound on little r. And then b is going to be our upper bound on little r. So we got the same sorts of boundaries that we saw before. Theta's bounds will be alpha and beta, so that's good. So this is how we're defining our polar rectangle. Once again, r is going to range from a to b, theta is going to range from alpha to beta. We're also going to have following condition. We're going to have beta minus alpha greater than or equal to 0, less than or equal to 2 pi. Basically, what this guarantees is that beta is going to be at least as large as alpha, and you're not going more than a full revolution. So that's pretty important to keep in mind. Then what's going to happen is our double integral over r of f of xy dA is going to be the same thing as, we'll have this outside integral from alpha to beta, inside integral from a to b, and we'll have f of r cosine theta comma r sine theta r dr d theta. So once again, this r dr d theta is actually going to correspond to our differential of the area. And then we're plugging in, we're basically using the conversion equations that I had up earlier, where x is equal to r cosine theta and y is equal to r sine theta. And then in terms of polar coordinates, this polar rectangle, you have theta ranging from alpha to beta, you have r ranging from a to b. So everything is consistent and working out exactly the way we're hoping for it to. Now, in terms of the theory that kind of led us up to this, I'm not incredibly worried about your ability to, let's say, prove this on a test or anything like that. Understanding the theory, I think, is very important, but at the same time, when you're tested on this stuff, what's going to really be the determining factor here is, are you able to apply the theory? And I have to say that when you're doing these conversions from rectangular polar coordinates, one of the things that I've noticed that sometimes will give people a little bit of trouble is, how do I take this region, how do I describe it in terms of the bounds on r and theta? So we're going to be taking a look at several different examples, and we'll get some practice with the ins and outs of these types of problems. All right, so let's take a look. We're going to have the double integral over r of 3x plus 4y squared dA. Now, of course, we need to know how r is described. So r is going to be the region in the upper half plane that's going to be bounded by two circles. So you have x squared plus y squared equals 1. And you'll have x squared plus y squared equals 4. Now keep in mind, x squared plus y squared equals 1 is a circle of radius 1 centered at the origin. X squared plus y squared equals 4 is a circle of radius 2 centered at the origin. And so what we're going to need to do is figure out, what does this region look like, and what are the bounds going to look like in terms of r and theta. So a good idea is to actually draw the region if you can. And so what you're going to have here is a picture that looks something like this. Once again, the x squared plus y squared equals 1, circle of radius 1, center at the origin. But keep in mind that what we're actually interested in is just the upper half part of this. The x squared plus y squared equals 4, well, that's going to be a circle of radius 2, center at the origin. But once again, we're just looking at the upper part of this. Now, once again, r is the region in the upper half plane bounded by these two circles, which means that r is actually going to be the shaded region here. Okay, so that's going to be our region r. What we have to do is think about, well, what are the bounds going to look like? What are the bounds on little r? And what are the bounds on theta? But what you have to keep in mind is that when you take a look at the shaded region, every single point is going to be from 1 to 2 units away from the pole. Also, if you think about the shaded region, it's going to get traced out as our theta value goes from 0 all the way around to pi. So that means that when we take a look at the description for capital R, you're going to have little r ranging from 1 to 2, and you're going to have theta ranging from 0 to pi. Pretty nice limits of integration. Certainly better than what we would expect using the rectangular coordinates. So now what we have to do is figure out, well, how exactly is it that we're going to evaluate this double integral? Now, keep in mind that we don't really want x's and y's showing up. We want to transform everything in terms of little r and theta. So we have to keep in mind that this double integral over r of 3x plus 4y squared dA is really the same thing as, well, we're going to have theta ranging from 0 to pi, so those are going to be our outside limits of integration. We're going to have little r ranging from 1 to 2, those will be our inside limits of integration. And then we have x is the same thing as r cosine theta. We have y is the same thing as r sine theta. And then the dA, remember, that's the same thing as our r dr d theta. So don't forget this extra r that shows up. It's very easy to forget. So this is what our double integral is going to look like in terms of polar coordinates. Now, it's certainly helpful to try to simplify this a bit, or maybe expand out this r sine theta raised to the second power, multiply through by r. And so if we do this, the 3r cosine theta, yeah, that gets multiplied by r. That's going to give us a 3r squared cosine theta. And if we were to multiply this through, we would have 4 times r squared sine squared theta. Multiply by this r, and we actually end up with 4r cubed sine squared theta. And we're integrating first with respect to r, and then with respect to theta. This works out pretty well, because if we're integrating with respect to r, remember, theta gets treated as a constant. So the cosine theta is really just a constant multiple times the 3r squared. Sine squared theta, once again, is just a constant times the 4r cubed. So when we go to integrate with respect to r, the 3r squared is actually going to be turning into r cubed. The 4r cubed integrates to r to the 4th. And we have to take this from r equals 1 to r equals 2. Now, we have to plug in the 2 for r, and then subtract what we get when we plug in 1 for r. Now keep in mind that if we plug in 2 for r, 2 cubed is going to give us 8. We'll have cosine theta. 2 to the 4th gives us 16. And that'll be times sine squared theta. Then we have to subtract what we get when we plug in 1 for r. Plugging in 1 for r just gives us cosine theta plus sine squared theta. We have some like terms to combine, but what we end up with is the integral from 0 to pi. We'll have a 7 cosine theta plus a 15 sine squared theta, and that's how it'll unfold. So let's make a little more room. So this will be equal to integral 0 to pi. Once again, 7 cosine theta plus 15 sine squared theta d theta. All right. Once we get it to that step, what we have to keep in mind is that, yes, we have to integrate with respect to theta, which means, in part, integrating the sine squared theta. And that's not exactly the most fun thing in the world to do. It does require us to start thinking about how can we change this form. But we do have an identity, and that identity tells us that the sine squared of theta, same thing as 1 minus cosine 2 theta divided by 2. So we're going to end up substituting that in for the sine squared theta. So we'll have integral 0 to pi, 7 cosine theta plus 15 times 1 minus cosine 2 theta divided by 2 d theta. And one of the things to keep in mind is that both the 1 and the negative cosine 2 theta get divided by 2. So if we want to, we could say that this is the same as the integral 0 to pi. Take the 1/2, multiply by 15, that gives you a 15 halves. So we'll have a plus 15 over 2. And then the negative cosine 2 theta over 2 times 15 will give us a negative 15 halves cosine of 2 theta. At this point, we have something that we can integrate without too much difficulty. And that's a good thing. So, we go about performing this integration. 7 cosine theta, integrate that, you get 7 sine theta. 15 halves, integrate that, you get 15 halves theta. And then the negative 15 halves cosine 2 theta, well, keep in mind that integrating cosine 2 theta, we've done stuff like this quite a few times, that's going to end up getting us a 1/2 sine 2 theta. So when we take negative 15 halves times a half sine 2 theta, we end up with a negative 15 fourths sine 2 theta. Now we got to take this from theta equals 0 to theta equals pi. And this works out incredibly well. Because keep in mind that if theta is equal to pi, okay, you got 7 sine pi. Sine pi is 0. You got negative 15 fourths sine 2 pi. Hey, sine 2 pi is 0. We're also going to have to plug in 0 for theta. Okay, well great. Sine 0 is 0. Sine of 2 times 0, hey, that's 0. So really all that we take from this is the 15 halves theta with pi plugged in. Because we plug in 0 for theta, we're still getting 0. So it turns out that just about everything zeroes out. All we do is end up plugging in pi here to get 15 pi over 2 as our final answer. So not too bad of a final answer. That's actually pretty good. Now, from here, we're going to take a look at another example. With this example, we'll be finding a volume. So we'll find the volume of the solid. And one of the boundaries for this solid will be the plane z equals 0, or the xy plane. And the other boundary will be the paraboloid. Z equals 1 minus x squared minus y squared. Now remember, this paraboloid is one of our quadric surfaces. Should have some familiarity with it. But if you want to get an idea of what this solid looks like, then we can certainly try to draw a picture of it. And so let's say we have our x-axis here, y-axis here, and z-axis there. And we'll go 1 unit, and another unit here, and then we'll go up 1 unit like so. Now, keep in mind that one of the nice ways to try to draw these is to think about the traces. So what sort of situation are you going to be in if you set one of the variables equal to 0? That is, if we want to figure out what the intersection of this paraboloid is in the xy plane. Well, we would have z equals 0. That would give us 0 as 1 minus x squared minus y squared, or x squared plus y squared equals 1. Well, that circle of radius 1, center at the origin. That's pretty good. So we'll have a picture that looks something like this. This will be our trace in the xy plane. And then we start thinking about, well, what would the trace in the xz plane be? And in that case, you would have y is equal to 0. So you'd have z equals 1 minus x squared. Okay, well that's a parabola. Basically z equals negative x squared shifted up 1 unit along the z-axis. And we would have a Picture looks like this is our trace. And then finally, if you were to take a look at the trace, what is the intersection in the YZ plane? If we set x equal to 0, you'd have z equals 1 minus y squared. So, you know, a similar kind of situation here. So if you take a look at what this solid would be, we're looking at a picture that's something like that. Well, let's consider what the region is that this solid lies over. Well, we got that from the trace, this intersection in the xy plane. This solid is lying over this circle of radius 1, centered at the origin. So if we think about our region R, over which the solid lies, once again, radius 1, centered at the origin. So if this is our region R, and R is going to be bounded little r-wise from 0 to 1, and then theta-wise from 0 to 2 pi. So that's the region over which this solid is lying. The question then becomes, well, how exactly is it that we're going to set up our volume, double integral for the volume of this solid? Well, remember, our volume is going to be the double integral over this region of, well, we typically would say we have z equals 1 minus x squared minus y squared. Okay. But think about this for a moment. If we're having a look at 1 minus x squared minus y squared, okay, well, 1 minus x squared minus y squared is the same thing as 1 minus the expression x squared plus y squared, which would be the same thing as 1 minus r squared, because remember the conversion equation, x squared plus y squared equals r squared. So when we think about this volume, we're actually going to get, well, you've got the integral 0 to 2 pi on the outside, integral 0 to 1 on the inside, 1 minus x squared minus y squared, same thing as 1 minus r squared, and then the dA is the same thing as r dr d theta. So that works out really well if we take a look at this in terms of rectangular coordinates. I'm sorry, polar coordinates. Well, we can multiply through by the r here, and if we do that, once again, we'll have volume as the integral 0 to 2 pi on the outside, 0 to 1 on the inside. We'll have r minus r cubed, dr d theta. We have to integrate with respect to r on the inside. And so that's going to give us a 1/2 r squared minus a 1/4 r to the 4th. All right. Fortunately, our limits of integration, r-wise, are really nice, because we have to plug in r equals 1 first. That'll give us a 1/2 minus a 4th, which is a 4th. And you subtract what you get when you plug in 0, well, you'll just be subtracting 0 then. So this turns out to be the volume is equal to integral 0 to 2 pi of 1/4 d theta. So really nice. It doesn't get much better than that. So our last bit here is going to be to integrate this 1/4 with respect to theta. And that will give us v is equal to 1/4 theta, taken from 0 to 2 pi. Plug in the 2 pi for theta, 4th times 2 pi, gives you pi over 2. So the volume of that solid that we have here will be pi over 2 cubic units. Right, so the next thing that we need to think about is the following theorem. See, it might not be the case that the region you're integrating over is a polar rectangle. So maybe you have some sort of continuous function f. So over which region is this function continuous? It's going to be some polar region. And we're going to see how the boundaries work for this. So let's call this region D. And this region D is going to consist of all points, first coordinate r, second coordinate theta. Now we are going to have constant bounds on theta. We'll have alpha as a lower bound, beta as an upper bound. But instead of having constant bounds on r, little r, what we're going to do is say that little r is bounded by some h1 of theta and h2 of theta. Now, we have to keep in mind that what this is going to turn into. So we take a look at the double integral over d of f of x, y, dA. And that's going to equal. On the outside, we'll have alpha and beta as limits of integration. On the inside, we'll have h1 of theta as the bottom limit of integration. h2 of theta will be the top limit of integration. And then this f of x, y, dA, well, remember, we want to make sure everything is in terms of r and theta. And so what will happen is we'll have f of r cosine theta, comma r sine theta. But remember the dA, same thing as r, dr, d theta. So the question is, what exactly happens if we are taking a look at a double integral over one of these regions that perhaps isn't a polar rectangle? And that's what the next couple of examples are about. And so for this example, we're going to use a double integral. And we're going to find a certain area here. So we're going to use a double integral to find the area enclosed. By one loop of a Rose curve. And this will be a four-leaf Rose curve. This will be given by r is equal to cosine of 2 theta. Now, back in Calculus 2, we take a look at how to draw these different polar curves. But one of the things that you run into time and time again are these Rose curves. And in particular, we have r is equal to cosine 2 theta here. Now, it's a good idea to try to draw a graph of at least one loop of this Rose curve. Now, one of the things you might remember is that when you take a look at this r equals, let's say, cosine of 2 theta, one of the loops is actually going to be symmetric about the polar axis. And so what we need to do is figure out the different theta values that are going to give us r equals 0. In fact, consecutive theta values that are going to give us r equals 0, so that we can figure out where we can open and close one of the loops. In particular, I want to open and close a loop that goes along here. Well, we know that the cosine of negative pi over 2 and the cosine of positive pi over 2 are both equal to 0. So if you think about cosine negative pi over 2 is equal to 0. Cosine of positive pi over 2 is equal to 0. Those are consecutive angles where your cosine value is equal to 0. But imagine what happens if 2 theta is negative pi over 2. That's going to mean theta is negative pi over 4. So once again, if 2 theta is negative pi over 2, theta is going to be negative pi over 4. And what's more is if you take a look at 2 theta being pi over 2, then yeah, theta is going to be pi over 4. And so one of the things that's really nice about this particular curve is that one of the loops is actually going to get traced as we move theta between negative pi over 2 radians, or sorry, negative pi over 4 radians, and positive pi over 4 radians. And the length of the loop is going to be 1 unit. And these radial lines are actually going to be tangent to the curve at the pole. So think about how much area this loop is enclosing. And that's what we're going to be taking a look at. Now we can use symmetry to our advantage. For example, we know that as theta ranges from 0 to pi over 4, we will be taking a look at the area that's in the top half of that loop. We can do that if we want to. We can take a look at that area and then double it. Or we can simply just take a look at going from theta equals negative pi over 4 to theta equals positive pi over 4, and the loop will get traced out as theta ranges over those values. Now, think about this for a moment. If we were to say that this region that we see right here is bounded theta-wise from negative pi over 4 to positive pi over 4, and that little r was bounded by 0 and 1, we wouldn't be describing this region. We would actually be describing a region that goes between these theta values, but the radius would be constant. This outer boundary, the radius would be constant at 1 the whole time. We would actually be looking at a sector of a circle. In fact, a quarter circle, as a matter of fact. So we don't really want to think of our region bounded that way because it's incorrect. However, notice that as theta ranges from negative pi over 4 to positive pi over 4, if you take a look at different radial lines that are in between, what's going to happen is these different r values that you get along the different radial lines are going to vary all the way from 0 to 1. So different radial lines are going to have different bounds on r. Well, what's the common theme, though? What is that upper bound? Well, the upper bound is given to you right here. It's going to be cosine of 2 theta. So if I take some radial line that's between negative pi over 4 and positive pi over 4, and I figure out, okay, well, what are the different possible r values for points along here in the region? Well, the smallest r value we can have is 0, but the largest one is going to be bounded by cosine of 2 theta. So we take a look at this region here, and we say, let's define it. We're going to say that little r is going to be bounded by 0 and cosine of 2 theta. And theta, of course, will be bound by negative pi over 4 and positive pi over 4. So those will be our limits of integration. Little r from 0 to cosine 2 theta, and theta from negative pi over 4 to positive pi over 4. So if you think about this as our region D, so to speak, let's say that's our region D, then we take a look at the area of this region. Well, remember, the area of the region is going to be the double integral over D of 1 dA. But think about what dA is in terms of polar coordinates. It's r dr d theta. We know what the limits of integration are supposed to look like. And so we'll take a look at working this through over here. Clearing off some room. and we'll have area is equal to, well, you got your negative pi over 4 to positive pi over 4 on the outside, as limits of integration. On the inside, you have 0 and cosine of 2 theta. And the dA, remember, is r dr d theta. Okay. So, when you go to integrate r, you're going to get a half r squared. We plug in cosine of 2 theta for r, we subtract what we get when we plug in 0 for r. But keep in mind, plugging in 0 for r, yeah, it's just going to give us 0. So we've got the area is going to be the integral negative pi over 4 to positive pi over 4 of 1/2 cosine squared 2 theta d theta. So cosine 2 theta gets plugged in for r. That's the same thing as cosine squared 2 theta. And if you remember from Calculus 2, finding the area of a region like this using polar coordinates, remember what that was. If you don't, no worries, I'll show you. Remember the area was integral from a to b of 1/2 r squared d theta. What is this? Same stinking thing. It's just your a is negative pi over 4 and your b is positive pi over 4. So it goes back to what we've learned before back in Calculus 2. It's all consistent. That's a good thing. Now, when we take a look at this area, once again, we've got to integrate cosine squared of 2 theta. Probably not the most fun thing in the world to do, but hey, you know, we can still work through it. Not a problem. What we need to do is go back to a familiar identity. And so that familiar identity that we have is going to be cosine squared x. It's 1 plus cosine 2x divided by 2. It's just that x is going to be 2 theta in this case. Well, that means our area is going to be integral negative pi over 4 to positive pi over 4. We'll have a half times 1 plus cosine of 4 theta over 2 d theta. Remember, if x is 2 theta, 2x is going to be 4 theta. So that's how we're getting this. The 1/2, and you got a 2 in the denominator here, so you can multiply these together. You'll have a fraction of 1/4, which you can always pull out to the outside. And then you'll have the 1 plus cosine 4 theta to integrate. Now we've already integrated stuff like this in this particular section, so it continues. We'll have area is the same thing as 1/4, and now we integrate the 1 plus cosine 4 theta with respect to theta. Integrate the 1, yeah, you get theta. That's good. Integrate the cosine of 4 theta, and you're going to get a 1/4 sine 4 theta. We're taking that from negative pi over 4 to positive pi over 4. Now, here's the really nice thing. If you plug in pi over 4 for theta here, you get sine of pi, which is 0. You plug in negative pi over 4 for theta, you get sine of negative pi, also 0. So what's going to happen is this. We're going to get the area is equal to 1/4 times, well, we plug in the pi over 4 for theta, and then we subtract 1/4, and then we plug in the negative pi over 4 for theta. Because once again, plugging in pi over 4 for theta, plugging in negative pi over 4 for theta here, is going to either give us sine pi or sine negative pi, both of which are equal to 0. Well, with that in mind, you'll get a pi over 16 plus a pi over 16. And if you add those together, you get 2 pi over 16, same thing as pi over 8. So that is the area enclosed by one loop of this rose curve r equals cosine 2 theta. All right, we got one more example to take a look at before this section is finished. So for this final example, we're going to find another volume. Now this time, this will be a volume of a solid. And it lies under the paraboloid z equals x squared plus y squared. Above the xy plane. And it's going to lie inside the cylinder x squared plus y squared equals 2x. Alright, so you're going to have this paraboloid z equals x squared plus y squared. You're going to have a cylinder x squared plus y squared equals 2x. Now, that cylinder is kind of going to be off-center from the z-axis, but I'll show you what it actually looks like. But our goal is to figure out what the volume of that solid looks like. And you can always look in your book to take a look at the a figure that's described by this. So let's think about the x squared plus y squared equals 2x for a moment. Now, if you take a look at x squared plus y squared equals 2x, remember, x squared plus y squared is equal to r squared, and then x is equal to r cosine theta. So we could look at this as r is equal to 2 cosine theta when we divide both sides of that equation by r. So r equals 2 cosine theta. But there is another way. If we want to stick with rectangular coordinates, we could also say, well, we've got x squared plus y squared equals 2x. So x squared minus 2x plus y squared is equal to 0, just subtracting 2x from both sides of the equation. But if you take a look at the x squared minus 2x, we're thinking, let's complete the square. So you'd have x squared minus 2x plus 1. Got to take half the coefficient of x and square that. Half of negative 2 is negative 1. Square it, you get positive 1. But if we added 1 to the left side of the equation, got to add 1 to the right side as well. So this x squared minus 2x plus 1, same thing as x minus 1 raised to the second power plus y squared equals 1. Now, this is a circle, radius 1, and it's centered at 1, 0. Okay, so that's what I was mentioning just a bit earlier, that the cylinder isn't going to be centered about the z-axis. It's actually going to be a bit off-center. It's going to be centered at 1, 0. So we think about how that cylinder is going to intersect this paraboloid z equals x squared plus y squared. Going to form the solid that's bounded below by the xy plane. And now we just got to figure out, okay, well, how exactly is this going to work? All right, how exactly is this going to work? Well, if you think about this circle, radius 1, centered at 1, 0. What you may notice is that that circle is actually going to get traced out as you go from negative pi over 2 to 0 and then to positive pi over 2. So once again, as we trace out negative pi over 2, take a look at these different radial lines that we would get going from negative pi over 2 all the way around to positive pi over 2. You're going to trace out that circle exactly once. So that's actually going to give us bounds on theta. So we think about this as our region D. We'll have theta bounded by negative pi over 2 and positive pi over 2. And we're going to have R. It's going to be bounded by 0 and, you guessed it, 2 cosine theta. Alright, so that's how our region D here is defined. So when you go to figure out the volume, got to remember top boundary, well, that's going to be your z equals x squared plus y squared. Okay, well with that in mind, got our limits of integration, got the function that we want to integrate. That's good stuff. So the volume is going to be double integral over d of x squared plus y squared dA. What you have to keep in mind is that x squared plus y squared, same thing as r squared. Also, dA is r dr d theta. Limits of integration, theta-wise, we've got negative pi over 2 to positive pi over 2. R-wise, we're going from 0 to cosine theta. Once again, r squared times r dr d theta. Now, of course, r squared times r, same thing as r cubed. Still have the limits of integration on the outside, negative pi over 2 to positive pi over 2. Inside, 0 to 2 cosine theta. This is r cubed. That will integrate with respect to r. And then once we get the inner integral figured out, integrate that result with respect to theta from negative pi over 2 to positive pi over 2. All right. The r cubed is going to integrate to 1/4 r to the 4th. And we take that from r equals 0 to r equals 2 cosine of theta. Now, we plug in the 2 cosine theta for r, subtract what we get when we plug in 0 for r. And so we'll have the volume, it's integral, negative pi over 2 to positive pi over 2. Now, if you plug in 2 cosine theta for r, 2 to the 4th is going to give you 16, and a 4th times 16 gives you 4. And then we'll have the cosine 4th of theta. Cosine theta raised to the 4th power, cosine to the 4th of theta. But we've got to use that same sort of identity we saw before. Now keep in mind, we know that cosine squared theta is 1 plus cosine 2 theta divided by 2. But cosine of the 4th theta is cosine squared theta squared. So what we're going to do here is we're going to replace once again cosine 4 theta, same thing as cosine squared theta squared, and then we can plug in the 1 plus cosine 2 theta over 2 for the cosine squared theta here. All right, so let's keep in mind what that really means. We have this expression raised to the 2nd power, so we got to square the top, put it over the square of the bottom. Now, that's going to give us v is equal to integral negative pi over 2 to positive pi over 2, 4 times 1 plus cosine 2 theta squared over 4. 4 is going to reduce out. So we can reduce out the 4's, but we can also expand out this 1 plus cosine 2 theta squared. And if we do, we'll square the first term, gives us 1. Multiply the 2 terms together and then double, that gives you a 2 cosine 2 theta. And then we square the last term, that'll give us a cosine squared of 2 theta. To handle the cosine squared of 2 theta, we'll use basically the same idea. It's just we'll have 2 theta here, so we'll have 4 theta there. So volume will be integral negative pi over 2 to positive pi over 2, 1 plus cosine 2 theta plus 1 plus cosine 4 theta divided by 2 d theta. If you take a look at this part here, got a half plus half cosine 4 theta. And the 1 plus a half, well, you can add those together, they'll give you 3 halves. So the volume is going to be integral negative pi over 2 to positive pi over 2. 3 halves plus 2 cosine 2 theta plus a half cosine 4 theta d theta. All right, so now we're ready to integrate. We know how to integrate things like cosine 2 theta and cosine 4 theta. So the volume is going to be, when we integrate the 3 halves, we'll get a 3 halves theta. Then the 2 cosine 2 theta, integrate that, you get 2 times sine 2 theta over 2. Okay, that's just sine 2 theta. And then you'll have the 1/2 times sine 4 theta over 4. That'll give you 1/8 sine 4 theta. And remember, theta is ranging from negative pi over 2 to positive pi over 2 here. Well, if you plug in pi over 2 for theta, let's say here and there, 2 times pi over 2 gives you pi, and we know sine pi is equal to 0. 4 times pi over 2 is 2 pi, and we know sine of 2 pi is equal to 0. If you plug in negative pi over 2 here, you get sine of negative pi, that's 0. Plug in negative pi over 2 here, you get sine of negative 2 pi, that's also 0. So it turns out that the volume is actually going to be 3 halves times pi over 2 minus 3 halves times negative pi over 2. So this gives you 3 pi over 4 plus 3 pi over 4. That's 6 pi over 4. Same thing as 3 pi over 2, which is your final answer. And that's how it ends. Recommended exercises from section 15.3. Let's take a look at 5, 7, 9, 11, 15, 19, and 25.